Please go ahead.
I was saying, feel free to interrupt or type in the chat if you have any questions during the presentation or during the class, and then I will respond to them at the end. Or if it's really a burning question, you can interrupt me midway and I respond. Yes, so let's first remind ourselves on what you have been going through. You learned that remote sensing is about obtaining data or information about the Earth's surface or different phenomena, but without being into direct contact with it. And in this case, you're using instruments or applications to record this data. You can use the aeroplanes, you can use the satellites, you can use the drones that are now very common currently in data collection. You can use cameras, etc. So all that, as long as you're not in direct contact with the phenomena, then you're doing what we call remote sensing. And this is what discussed at the start of the module. You also discussed that since you're using different sensors to capture this information, you're capturing it at different levels. It can be on ground, or it can be aerial, or you're using space, which is the settle. The higher you go off the ground, the larger coverage you're able to cover. But however, it means that you're going to cover little detail, or within that coverage that you're having, the satellite, there is little detail that you can distinguish. Whereas with the use of the aircrafts or drones, you're covering a smaller area, but then you're having a lot of details. Each sensor or each platform that you're using to capture this data has its own advantages and disadvantages, like we shall see during the discussions. And these guide you on which platform to select basing on the kind of project or application that you're dealing with. Yeah, so you also learned that with remote sensing, these sensors have bands that record data in different regions of the spectrum. And with this, what you already discussed, so that with optical remote sensing, you're mainly utilizing the visible and the near infrared band. These measure reflected radiation or reflected energy. So what we are going to look at, we are looking at the thermal infrared region, which is only measuring emitted energy. And that is what we are going to look at today, which is the thermal remote sensing. So thermal remote sensing is about collecting data and processing it, utilizing the thermal infrared region of the electromagnetic spectrum. And in here, we are not interested in how much energy is reflected, but we are only interested in the energy that is emitted from the ground by different objects or phenomena. Thermal remote sensing, we are not looking at the reflected sunlight, so that means that even during the night, we can have these images. However, I must add that for these images to be captured at night, or to have thermal remote sensing at night, this emitted energy must be strong enough for it to be measured by the sensors. So that is the only possible way of how we can have thermal remote sensing at night. Most of these sensors that record at night will be active sensors. But with our passive sensors, most of them, since they depend on the sun as a source of radiation, then you will have data only captured during the day. So energy will be emitted during the day, and thus we can have information about the ground during the day. With thermal remote sensing, the principle behind it is that every material on the surface of the earth, whether humans, whether buildings, whether pavements, whether trees, whether vegetation, everything, as long as it has a temperature above zero, then it emits radiation. And it is that amount of radiation that determines the temperature of these materials or objects. So objects or materials that have higher temperatures will emit more radiation as compared to the cold or the warm body. So in thermal remote sensing, we are looking at heat radiated by these surfaces, and it is the main source of data. Like we have said from the start, we are not measuring reflected energy when we talk about thermal remote sensing. We are only looking at energy that is emitted. I hope we are together. You get lost somewhere, kindly let me know so that I rectify something or I make you to the same level with the rest. So we have been talking about electromagnetic radiation, but in this case, we are only concentrating on thermal radiation. And we have already said previously, thermal remote sensing, we are utilizing the infrared portion of the electromagnetic. However, I want to first let you know that actually the infrared region quite big, so it ranges from around 0.6 6 micrometers to around 1,000 micrometers. So it's a very large region of the electromagnetic spectrum. It comprises mainly of 4 portions, which is the near infrared, the short infrared, the thermal infrared, and then the far infrared. The near infrared and short infrared is what you looked at in the optical remote sensing. This detects reflected energy. And what we are looking at today is the thermal infrared, which is between 3 to 14 micrometers. And this is where the emitted energy is measured. However, we also have the far infrared, which is between 14 micrometers, about 1,000 micrometers. This is, however, not used within remote sensing. It is for other applications like astronomical, because much of the radiation here is absorbed by the Earth's surface. So there is a lot of absorption, so remote sensing cannot take place in that part of the spectrum. This thermal radiation, like we have already said previously, it ranges from 3 to 14 micrometers. However, what we should note is that not this entire region can be used for thermal remote sensing. And this is because there is absorption, and then there is absorption, which what we call the absorption windows, and also the atmospheric windows. Like you see on the image displayed, this is the thermal infrared region between 3 to 14 that we've said where thermal remote sensing takes place. But as you can observe, between around 5 to 7, there is absorption. So in that absorption window, thermal remote, we cannot have data being acquired in that case, because much of the radiation is absorbed by gases and water vapor. So within the atmospheric window is where the thermal remote sensing takes place. And this is mainly between around 8 micrometers to around 13. So that is where much of the remote sensing takes place within the atmospheric window. However, you can also see that not all energy is actually recorded by the sensors. Not all energy emitted is recorded by the sensors. Still, there are windows of absorption whereby the gases like carbon dioxide and ozone really do absorb this radiation. So not all of it can be measured by the sensors. Therefore, there is no region within the electromagnetic spectrum that has 100% or that supports 100% remote sensing. However, these regions have different levels. There are levels that are high, that whereby most of the emitted energy is recorded by the sensors, and then there is where the lowest energy is recorded by the sensors. And where the lowest energy is recorded, that means there is a lot of absorption taking place, and those are the absorption windows where we do not have information being recorded by the sensors. And where most of the energy can be recorded by the sensors is within the atmospheric window, where there is little absorption of this emitted energy. Yeah, so the best principles or the best radiation principles that we are going to look at today are mainly two. However, I will implore you to read more to understand about these radiation principles. So, as we said within the introduction, that the emitted radiation determined by the temperatures or the kinetic temperatures of the objects that are emitting this radiation. Therefore, how much energy is radiated or measured by the sensor at different wavelengths will depend on the emissivity and then kinetic temperature. These are the two main factors that determine how much energy is measured or is recorded by the sensors during thermal remote sensing. So the first one we're going to look at is spectral emissivity of the surfaces. So emissivity just refers to the ability of a material or of a surface emit radiation as compared to a black body. A black body is a material or is a surface that emits 100% of the absorbed energy, absorbs energy from the sun and emits all of it. That is the perfect body. And that is what we call the black body. So, however, we know that materials or surfaces do not behave like black bodies like we saw. Some energy will be absorbed and some will be emitted. So not 100% emission and not 100% absorption. So that is what emissivity is. It is just the ability of a body to emit radiation as compared to that of the black body. So this black body radiation or black body principle can be more explained using this Planck's radiation law, Stefan Boltzmann's law, and Wien's law. And these are the laws I'm telling you to go read about. These laws relate the amount of energy emitted to the temperature of that. We have said that the black body is a perfect emitter of radiation. So meaning that all the energy that it absorbs, it emits it. But however, materials in nature are not perfect emitters of radiation. So these laws relate the emitted radiation of these bodies. So you can read more about these laws to understand the relationship between emitted energy and then temperature. So they can help you understand the idea of black body radiation. Same thing said differently, real objects or surfaces do not behave like black bodies, and this is because they only emit a fraction of the radiation. So not all the radiation is emitted, some is absorbed. So they do not behave like black bodies, which are perfect radiators. So that is the first principle that you need to understand, emissivity. The application of this, if you have an image, a thermal image, and you're trying to derive meaningful information out of it, you will need to correct these images for emissivity, because we have already seen that surfaces are not perfect emitters, or they do not behave like real bodies. So you must put into consideration that they are not perfect emitters, therefore they must be corrected for spectral emissivity. So this is one of the guiding principles when we come to thermal remote sensing. So what determines actually this emissivity, this ability of a body to emit radiation? One is the composition of that material, or the surface, composition of the surface. In here, we normally call it the roughness. Smooth surfaces will reflect more other than emitting, while rough will actually emit more energy. So the roughness of a surface will determine its emissivity level of that body, of that surface. Secondly is the moisture content, the field of view, and viewing angles. These determine the emissivity of, so clean and polished or metal surface have low emissivity. That means they cannot emit a lot of energy. Much of it is reflected, like I said previously, whereas rough surfaces will have higher emissivity value. So it is still explaining how emissivity affects the amount of emitted energy that is recorded by the sensor. So in here, I have put a table that shows different emissivity ranges. It says water, snow, human skin, ice, vegetation, wet surface, asphalt, concrete, etc. They do not behave like real bodies. They emit only a fraction of the radiation. Therefore, their emissivity values are less than 1. And these values, like I said before, they are used in correcting the estimated temperature values from thermal images, taking into consideration that they are not black bodies. If you have any questions, kindly put them into the chat. I'll be checking them out at the end of the session. So the second principle that guides us in thermal remote sensing is kinetic energy. In the introduction, we said the amount of energy emitted by a body is dependent on its temperature, and this temperature is the kinetic temperature. It's inside, or you can call it its body temperature. The body temperature is what determines the amount of energy that will be emitted by this. And this kinetic temperature is generated internally by each surface, or by each body. From physics, we know that each material has molecules or photons that interact, and in this interaction, temperature is generated, and this temperature is what forms the body temperature of that surface. So this body temperature is what affects the amount of energy that actually this surface can be able to emit. In reality, the temperatures measured by the sensor will be slightly correlated, or will be actually slightly lower than the kinetic temperature, because these temperatures measured by sensors are dependent on the temperature of the body that is emitting. So the higher the temperature of the body, the higher energy that will be emitted, and thus high temperatures will be recorded by the lower temperature of a surface or a body, the lower emission, and thus the lower temperature that will be recorded by. So kinetic temperature is the true temperature of the body, and this can be measured by thermometer in the normal conventional scales of Celsius or Fahrenheit or Kelvin. On the other hand, what the sensors measure is what we call the radiant temperature. So this temperature is from the emitted. So in remote sensing, we call this the brightness temperature of the surface. So the relationship between radiant temperature and kinetic energy is a positive correlation. It is a strong relationship between the two, because the radiant temperature depends on the kinetic temperature. when I talk of radiant temperature, I want you to know that this is temperature that the sensor is going to give you, and kinetic temperature is the true body temperature or the temperature of that surface. So these are the two things that you should put into consideration when you're doing thermal remote sensing. The first one, I repeat, is emissivity, and then the second is kinetic temperature. These two determine the radiant temperature that will be measured by. So we can move to look at some of the thermal sensors. There are very many, but these are some of them. First, we have the Landsat satellite. Landsat streams currently from Landsat 4 up to currently Landsat 9. So, and these satellites have instruments on board, carry different bands. For Landsat 4 to 7, the band that is responsible for thermal remote sensing is band 6, and that is the one that has the thermal infrared sensor. Whereas for Landsat 8 and 9, it has a thermal infrared sensor that carries two bands, and that is band 10 and band 11. And these are the two bands that are responsible for thermal remote sensing when you're utilizing the Landsat satellite. Another sensor that we have is MODIS, that is moderate resolution imaging spectroradiometer. This has actually very many thermal bands. As we can see, these are around 12 bands. So band 20 to 25 and then 27, 36 are all thermal bands. So when you're doing thermal remote sensing applications using MODIS satellites, then you will know that these are the bands that I can use for thermal remote sensing. Also, another interesting thing to look at is that these sensors have different resolutions, or spatial resolution. Also, the temporal resolution is different. As we shall see in the discussion that is coming up, we shall see how to trade off between spatial resolution and then also temporal resolution. But all we can see is that thermal bands are at 1 kilometer resolution, while Landsat satellite thermal band for band 4 to band 7, the thermal band is at 30-meter resolution. Okay, it is captured at 60-meter resolution, then resampled to 30 meters. So maybe I can show you where that. This is what I'm talking about. Landsat 7 to Landsat 5, they have the Landsat 5 4 to 7 have the same number of bands, which are 8 bands, and then it's only band 6 that is a thermal band. So it is at 60-meter resolution, spatial resolution, but resampled 30 meters. Whereas for Landsat 8 and Landsat 9, they have two thermal bands or thermal sensors. They take up band 10 and band 11. These bands are at 100-meter resolution. For MODIS satellites that I've already talked about, we are seeing its resolution at 1 kilometer. So they are at different resolutions depending on the application and coverage that you're looking at and how frequent you want the data. It is what will determine what kind of resolution to take up for your application. Another example of the sensor that we have is the visible infrared imaging radiometer suite, which is the VIRAS. It has 7 spectral bands, 7 thermal bands. The nomenclature, some are I bands and then some are M bands. M bands meaning the moderate resolution. So they are at 750 meters, that is 12 to 16. And then the imaging bands are at a much better resolution, which is 375 meters, and that is I4 and I5, meaning band 4 and band 5 within the VIRAS. Also, there is another, which is the ASTAR, AVHRR. So there are very many thermal bands, but what I'm trying to say is that your choice of the sensor will still depend on your application that you're going to carry out, the cost implications, and the coverage, or how frequent you want data. So the thermal bands or the thermal sensors are very many on board. Another thing that I should note here is that these are the same find in optical remote sensing. At the start, we said that within optical remote sensing, we are utilizing the visible and near infrared. These other bands listed here are the visible and near infrared and the shortwave infrared. They're the ones that measure reflected energy. On the same satellite, there is also another band, which is a band 6 that is doing emitted energy, and it is thermal band. So one satellite can have 2 types of remote sensing occurring. Can do both optical remote sensing and also thermal remote sensing. So there are no specific satellites for thermal remote sensing. Yeah, so after understanding what thermal remote sensing is, in what part of the electromagnetic spectrum it takes, what are the key guiding principles, and what sensors, or how can we get, where do we get this data from? We have known that we know the bands actually used when we are doing an application on thermal remote sensing. So the next thing we are going to look at now is how do we actually interpret these thermal? So the interpretation of these images, first and foremost, will be visual by just looking at the image. When you download it from the provider and you have it, you know that. Take an example, I have downloaded a Landsat image, and I know within a Landsat image, if it is Landsat 8 and Landsat 9, I'm going to look at band 10 and band 11. So when I look at band 10 and band 11, what do I see? What do I visually interpret? So most of these images, like I said, they are single band. One band, which is band 6, and then here band 10 and band 11, and they're always displayed in grayscale. So how you interpret this image by just looking at it is that where the image is lighter, it will be representing the object have warm temperatures or higher temperatures, whereas areas that are darker or that are a shade of black that is dark will be representing the cool area. That is the first way you can actually try. It's the first step to understanding or interpreting a thermal image. So this is exactly what I'm talking about. On my left-hand side, this is a natural color image utilizing the visible spectrum, the RGB. When you download an image, this is what you will see, first of all. When you use RGB, that is the red, green, and blue bands. So you'll be seeing it in its natural color. Water appearing blue, vegetation appearing green, etc. So this is what you're going to see in the visible spectrum. Whereas when we look on the right, this is a thermal band, and this is band 10. This is from a Landsat 8 image. So this is band 10. From what we saw on the previous slide, we say that the first step interpreting this thermal band or this thermal image is by looking at the grayscale level. Brighter areas will indicate areas that are warm, while the dark areas will indicate the areas that are cool. Simple analysis that, for example, that you can get from here. You see, water is appearing in the dark shade of black. So that shows that actually water is cooler than the surrounding area. Also, where you see this dark green, which represents, this is actually a national park, I think Atuhaire National Park, it is appearing dark. So vegetation actually has cool temperatures. So the thermal band is still telling you that this area, which in this case is a national park or a forest, actually has cool area. Another interesting thing that you're going to still use to understand your image, we are seeing this bright surface. And we say on thermal images, the brighter or lighter areas indicate areas that are warmer. And in this case, this area here is actually a settlement area. It has built up, and from what we have read in literature and even from experience of what is happening within the real world, built up areas have higher temperatures. So the thermal image is clearly telling you what is that. It's actually a built up area, and built up areas, because of the impervious surfaces, the emissions, this area has higher of temperatures compared to this area, which is actually a forest or a national park. Another interesting thing that I want you to draw, still trying to understand this image, is when you look at this image, you see, I don't know if it is very clear on your screen, but you see here is a burnt area, and this seems to be smoke coming out and diffusing to other areas. Very well capture it. You look at that area, it is very bright. It shows you that the temperatures within this location are very high. So by just looking at the image, not doing any analysis, any computations, you can already have an idea of what actually is taking place in this area. You can understand that actually places that have higher temperatures, and then the places that have actually cooler temperatures. I think George has a hand raised up. You can speak.
Yes, Jason, thank you. I wanted to make an inquiry.
Yes.
This kind of smoke,
Yes.
does it indicate high temperatures or does it indicate cloud cover?
No, this is smoke
Yes.
because from the RGB image, we are already seeing it is smoke. So it indicates smoke. I was actually coming to the next, how you differentiate clouds from this kind of smoke, which is indicative of high temperatures. So when you look at this area within the water, these are clouds here. Clouds in a thermal image appear very black because the radiation cannot penetrate. So these areas are perceived actually cool or cold. The cloud will absorb most of the energy that is emitted. So what the sensor will record will actually record very low temperatures. So that's why clouds will appear as cool within a thermal band or within a thermal image. I don't know, but I guess I've answered him. So how to differentiate smoke from clouds? Like I said previously, atmosphere absorbs. We said we have absorption windows and atmospheric windows. And within the absorption windows, much of the emitted radiation is absorbed. So less is recorded by the sensor. It applies in this case. The clouds, which contain actually water vapor, do absorb much of the emitted radiation. Therefore, less radiation is actually detected by the sensor from those areas. That's why where there are clouds, that area will appear black, indicating lower temperatures because most of the energy was absorbed by the clouds. And these clouds have water vapor, have gases that do absorb this radiation. Whereas if it is smoke, like we see here, it will still be indicative of the cool or the warm temperatures that are prevailing within that place. For example, we see here, there is a fire is indicated here, and we can see the brightness increasing. Even where there is smoke, it's still indicative of warm temperatures or high temperatures, and we still see the brightness in those areas. So that is how you differentiate smoke from clouds when you're having a thermal image. So we have said the first way to interpreting thermal images is looking at it visually, and you look at the grayscale level.
Christine, there's a hand up.
There is another hand up. Okay.
Hi, Christine.
Hi.
There are some messages, there are some questions in the message area, the chat area. Was asking 1 kilometer versus 100 meters resolution, which is better resolution?
So
that one we're not answering.
Who is that?
the professor says I first skip that question. Okay, I'll talk about it towards the end. It is okay.
Okay.
I hope you can hear what I'm saying. I'm hoping.
Okay, yeah. Okay.
Okay. Yeah, so what I was saying is in interpreting thermal images, the first thing we have looked at is looking at it through visual interpretation by looking at the grayscale levels. The second thing that we are going to look at in interpreting thermal images, you will interpret them depending on the time of the day at which those images were captured. So images captured at night or during the day will have totally different results. So when you're interpreting thermal images, first understand at what time was this image captured before coming up with conclusions that are not matching the times at which these images were captured. And this is because of these three factors. The first one is the conductivity, thermal capacity, thermal inertia. At different times of the day, these factors will influence the temperatures that the sensor is able to record. So thermal conductivity, we are looking at the rate at which heat passes through the material, and capacity is how well that material can store that. First, looking at conductivity, we know that metals are good conductors of heat. So meaning that metals emit more energy. So if a surface has higher conductivity, it means that the amount of energy or the amount of radiation emitted is also high and at different times. It can be a good conductor during the day and a bad conductor at night. So depending on its conductivity, depending on its capacity, like we saw, which is how well it can store this heat for a long time, it even means that at night it is actually able to still emit more energy. So meaning that still at night, the amount of energy recorded by the sensor is still high. Looking at inertia is how this material responds to different temperature changes. When we talk about time of the day, these factors do play. So if it is at midday, how a material responds to the temperatures at midday is different from how it responds at midnight. So when you're interpreting thermal images, look at the time of the day. At what time was this image captured? If it was captured at midday and another image captured at midnight, don't say that how come temperatures within one day were drastically decreasing like this, but just look at different times. At night, how do materials behave? Do they actually have a lot of energy they emit, or they absorb most of it? So if most of the energy is absorbed at night, meaning that the emitted energy will be very low. Hence, the energy measured by the sensors will also be low. And that's why you will have images captured at night having low temperatures, whereas images captured during the day, because there is a lot of radiations that is being emitted, those will be high temperatures. So when you're doing a time series analysis, put into consideration of the time of the day for you to come up with informed decisions. Otherwise, if you do not put into consideration the day or the time at which these images were taken, you may make wrong conclusions or wrong analysis on your data. So this is what I was talking about. When you download an image, there is always a metadata file. And this, from what you have studied, I'm sure from previous years, or last semester or last year, you studied about metadata. And metadata is data describing that data. So same thing. Satellite images or satellite data also has metadata. When you get an satellite image, the first thing to look at is its metadata file. So when you look at this metadata file, it will have the date at which it was captured and then the scene time, or the time at which this image was captured. So in this case, we are seeing we have the capture was in 2020, December 16th. The time is 8:07. Z means it is in UTC. So if that image is for Uganda, to add 3 hours. So meaning that this image was acquired at around 11 a.m. When you're doing analysis that involves very many images captured at different times, you will have to come to look at this. At what time were these images captured? And ensure that when you're doing your analysis, for you to compare temperatures, ensure that they were captured same time or within the same time frames. You cannot analyze a night image with a day image and then start making comparisons of which one is higher and which one is lower. That will not make sense. So time of the day is something that matters, and how you get to know it going through the metadata file. It will inform you the time at which these images were. Yeah. So those are the two main things now that you will use to interpret thermal images. However, if you want to do further analysis on thermal images, there is a lot of material that you can read about, or I'm also available if you really want to understand more or do research using thermal images. I'm available, but also there is a lot of literature that you can read about. But for now, for you to interpret firsthand when you look at thermal image, those are the two things that you need to look at: time of the day, and then also using the grayscale levels. Those two can already give you a picture of what is taking place within that area of interest that you're looking at. The next session, very short, we are also going to see when we are doing analysis of these thermal images. Yes, we have interpreted them, understood that these areas have higher temperatures, these areas have low temperatures. This is what is happening. But there are things that we need to consider or to put in mind while trying to come up with different conclusions or analysis. So the first thing to consider is that thermal infrared sensors actually had calibrate. And why is this so? Is because different surfaces have different emissivities. What I said previously is that for you to derive meaningful information out of a thermal image, you must correct for emissivity. But remember, different surfaces have different emissivities. So what kind of emissivity value or correction are you going to apply? So this is why thermal sensors are hard to calibrate. This is still an open area of research on atmospheric corrections or emissivity corrections for thermal remote sensing. So I may not say much because it is still an area of research that actually those of you who wish to have your research done in thermal remote sensing, you can look into it. It is still an open area of how to actually, the best way to carry out emissivity correction for temperature determinations for remote sensing. So it is an area that needs to be looked at, and it is one thing that you put into consideration. Even after you have applied, because there are very many emissivity corrections, after you have zeroed down and applied a certain emissivity correction, consider that it's actually not perfect because these are different, the image contains different surfaces, and you have applied a correction that is general. So to what extent that emissivity correction is good enough, I don't know. It is an area of research that you can explore. Secondly, the second thing to consider when you're analyzing thermal images is that the temperatures that the sensors are recording is surface temperature, just a few centimeters off the ground. I'll take an example, it's actually here, of water. The temperature of water measured by the sensors is actually surface temperatures, a few centimeters, about maybe 10, 15 centimeters from the surface of water. So you will have water temperature measured by the sensor being around maybe 20 degrees Celsius. Whereas when you actually go through into the deeper levels of the lake, actually the temperature is very low. This is because the sensors only measure surface temperatures. So this is also something that you need to consider, that the temperatures that you're getting from the sensor are not actually the true body temperature. They are just up to a certain level, up to a given depth, which is a few centimeters off the surface. And this is what I was saying previously. The kinetic temperature and the radiant temperature are related, but they are not the same, because the kinetic temperature is the true body temperature, whereas the radiant temperature is the surface temperature. In most publications or journals, you'll find it being called something like sea surface temperature, land surface temperature. So those are the temperatures that we are getting from the sensors, but they are indicative of what the true body temperature is. They are indicative, but they are not the true body temperatures, even if they are closely related or strongly related. Second thing, what I'm saying is, you put in your mind when you're analyzing that actually what I'm analyzing are just surface temperatures up to a little depth of about 15 to 20 centimeters off the surface of the material or of the water body. The other consideration that you should look at is when analyzing this data, they are also topographic. The way the area is topographically viewed affects the amount of affects how big or how low the temperatures will be recorded sensors. So what we are saying is that areas that are sloping or that have slopes may be shielded off from radiation, so they will actually appear cooler, while the slopes that actually receive direct sunlight will actually appear warmer compared to the others. So all these effects, the topographic nature of the surface, will affect the temperatures that are being recorded by the sensor. Also, another thing to put into consideration, like I had said previously, I think it is George who asked about clouds. Clouds and fog absorb radiation. That means that the temperatures emitted from such places will be warmer because much of the radiation has been absorbed by the clouds. I hope we are together. Yeah, so those are the few considerations. These ones we put them there for you specifically for people who want to go deeper and understand these thermal images, so that when you're carrying out your analysis, these things remain at the back of your mind, that there are actually factors that do affect these temperatures that you're getting from sensors. So they should remain at the back of the image of your mind when you're doing analysis or an application in thermal remote sensing. Yeah, so, and I think this will answer. George's hand is raised up. You're free to ask.
Yes, Ms. Christian, I'm inquiring, what are some of the application areas for the thermal
We are
remote
going
sensing?
to eat. We are going to eat. If you saw the presentation outline from the start, you should have seen applications of thermal remote sensing somewhere. So we are coming to it. So that's what we are going to look at. I'm sure it is going to answer one of the questions that I was told was in the chat, which resolution is good for your thermal remote sensing application. I will not say 1 kilometer or 100 meters is good, but what I will let you know is that how good a resolution is depends on these three main things. What scale are you working on? If you're working on an area that is global, if you're looking at an entire globe, of course, you know you will not achieve it with 100 meters resolution. So a kilometer resolution or a 5-kilometer resolution will be good enough. The details from a 5-kilometer resolution, if you're doing global, will be enough. So are you looking at regional? Are you looking at national, or you're looking at sites? So the scale at which you're working on determines the resolution that you're looking at. For example, for a site-specific scale, that means you need finer details. You need to understand the smaller details that are within that area. So a resolution of 5 kilometers will not give you that. That's when you'll go in for resolution of around 300 or 100 or 30 meters, because those give you finer details that are needed at such scale. Whereas when you're working with global, you may not need those small details, so you will go with a much bigger spatial resolution of about 5 kilometers. The second thing that you will consider when you're choosing the thermal sensor used in your application is how frequent do you need the data. Do you actually need to analyze satellite images on a daily basis? You need to analyze them over a fortnight. You need to analyze them weekly, seasonal. What time frame or what frequency are you looking at? And this takes us to the temporal resolution. So for you to analyze temperatures on a daily basis, that means you will go for sensors that have a temporal resolution of 1 day. So with these sensors, you will find that those are the ones that you can be able to give you data on a daily basis. However, what you should note is that a satellite that gives 1 kilometer resolution may not still give you a daily temporal resolution. It may give a spatial resolution of 30 meters, and yet the data can actually be available maybe after 2 weeks, each 2 weeks. So there is that trade-off. What do you want more? Are you looking at frequency, or you're looking at the area of coverage? It still zeroes down to what kind of application you're dealing with. I'll give an example. Landsat that has a spatial resolution of 30 meters for thermal bands, in this case, it is 100 meters. Its temporal resolution is 16 days, meaning that you can analyze this data every 16 days if you want a final resolution of 100 meters. However, if you want daily basis, there is MODIS satellite that we looked at previously. You have MODIS giving you daily images, but at a reduced resolution, which is 1 kilometer. So there is a trade-off. What should guide you is, what are you interested in? Are you interested in daily, or you're interested in the area of coverage, how much detail you want? So there must be a trade-off. If you want daily, then you'll go with MODIS that has 1 kilometer resolution. If you want weekly or fortnight, then you'll go with Landsat. Better spatial resolution, but temporal resolution is 16 days. So it still goes back to you, the researcher, or any application or project that you're working on. That's why I can't say this resolution is better than this. It still depends on what you're working. The third factor that you will consider while selecting these sensors is also how much the cost implication, depending on how much your project is going to cost you. Then you will look at how much do I need to get certain data. If you're okay with paying money, then you go for that sensor. If you're not okay with paying money, then you look at the freely available sensors, but you will need to trade off between the spatial resolution and the temporal resolution, like I explained. We come to the part that George was more interested in. So there are very many applications where you can apply these thermal bands or utilize thermal sensors, and I have put here these links. The publication is really so wide, so much. So when I give you these, maybe the lecture slides, you can read these papers, how people have applied thermal remote sensing or thermal images in various applications. But what I know, what you will maybe rhyme with at the moment, mapping urban heat islands or temperature changes. Lands, I'm sure you have heard of land surface temperature or sea surface temperatures. What this application is doing, you're looking at how temperature is changing over time, either on land or on water. So when you're doing on land or on water, then you're utilizing the thermal bands, because we said thermal remote sensing is about heat, it is about temperature. So anything temperature dynamics, you're looking at the thermal bands. Urban heat islands are derived from temperature dynamics. These are the two applications that I'm sure you easily understand. And maybe when we go to geology, maybe also wildfires, how you can check, you can look at extent of the burnt areas, or you can also be able to predict wildfires in a certain area using these thermal sensors. So the applications are very many. I will implore you to read as much as you can. I have put here links you can read through and see how different authors have utilized thermal bands to carry out different applications and come up with different conclusions and recommendations. So all this, what we are looking at, temperatures and how temperatures can be applied in making different informed decisions. So the applications are very many. I can't list them all here, and I can't explain all of them right now. So there are very many. I'll just implore you to read more about them if you want to know. So remote sensing, I'm sure what you learned from the start is remote sensing enables you to capture data on a large scale, to cover a larger area by capturing data that would not be actually possible when you're using measurement. So it applies both for optical remote sensing, thermal remote sensing, microwave, radar, etc. So as long as you're doing remote sensing, yes, you're covering bigger areas, but there are some limitations to it. So the first thing, like, okay, it is just actually like what we have been talking about, atmospheric interference. In the previous slides, we saw that actually clouds do absorb radiation, and so much of the radiation is not able to be recorded by the sensor. So those atmospheric interruptions are one of the limitations in applying thermal remote sensing or remote sensing in general. Therefore, there are atmospheric corrections that you need to apply to your data to have a reliable information. And this is what I was talking about, that the area of atmospheric corrections, which include the emissivity part of it, is a wide area of research that you can look at. So it's a limitation to remote sensing, but it's also an area where you can do research and understand more. The other limitation with remote sensing, or with thermal remote sensing in this case, is you will have a trade-off between the spatial and temporal resolution, like I have talked about. And then the other thing is that if you want to go for higher resolution, or maybe a meter resolution, that is if you're doing with radar that Professor said you're going to look at later, is you will need to put into the cost implication part of it. These sensors that I told you about, for these passive sensors, for thermal sensors, they're actually free of charge, but as you can see, the resolution, is debatable. So if you're looking for fine resolution, then the cost bit of it becomes a challenge. Also, Like any other method of data collection, you will need to carry out validation. So, and validation is done using in situ measurements. I'm sure most of you will know that if you're to get temperature data to validate your satellite information, it is a bit tricky because how many weather stations do you have in the country that will give you temperature information? I don't know. Availability of validation data is a limitation when you're using remote sensing data. How valid your results are is also debatable, which is the same thing to deal with the ground data availability. You may have, yes, the stations spread out, some are there, but how have that data available to you? A lot of politics, getting data from meteorological centers is not easy. So it becomes a limitation when you're actually doing remote sensing application. These cut across thermal remote sensing, optical remote sensing, and any other data collection method that you choose to employ or use in your project. Or maybe I can check out the question if there are any questions in the chat. I don't know if there is anyone with hands raised up. I think
Hi,
Aisha.
Christine.
Hi.
Yes. I wanted to know the applications of this thermal sensors. In geology, I'm a geologist. Can we apply it in underground or under surface mapping, mineralization that actually happens underground?
No, you see, one thing that I said during the discussion is temperatures measured by the sensors are up to a certain depth. Their surface, it is surface information, it is surface temperature. So for underground measurements, then you will need to employ other techniques that actually penetrate further than the surface measurement. So in this case, these bands will not give you much of what is actually underlying the ground, but they can give you an impression of what is possibly there, but they will not give you the clear data or information of what is underground, maybe 5 meters underground. This is a surface measurement of up to a few centimeters above the ground.
Okay, well noted.
Yes, George?
Yes, thank you. I'm inquiring what kind of projects can you do research on using this? You're like a plan B person.
So I don't know how to answer that because I cannot say this is a project, but like I said, for you to determine what you can do in thermal remote sensing, first of all, what you will need to do, go and read about what people have done, and then look at their recommendations. It can be a method like, okay, how do I say? It can be a method that they used. For example, if you have a satellite image, no data is recorded in digital number values, and then you transform your digital number values into temperature values. So that kind of conversion, you apply different algorithms. So maybe you could look at it of these people have actually used this algorithm. Maybe there is another algorithm that you could develop to see how it works out. So I cannot say do this or you're going to do this, but the best way is to do literature review, see what other people have done, and then determine the gaps that are in there. What gaps can you see, or what have they recommended other researchers to do? So from the gaps, then you develop your project.
Okay, thank you. Maybe the other question was, there was a slide about metadata. Inquiring, how do you get that metadata about the image?
Oh, so have you ever downloaded a satellite image?
Yes.
Yeah. So that is very good. If you download a satellite image, it will come as a zip folder.
Yes.
Yeah. So in that, when you unzip, there are very many files, the bands, and then there is you will find a notepad file, MTL text file. So that text file, that MTL file is the metadata file. So it's a notepad file. I don't know if I can open one of them directly, maybe. Let me see. Yeah, so this is an unzipped folder of certain data that was acquired in 2014. These are bands. And then I think you can see this file that I'm pointing at that has an MTL extension. It's a text document. Can you see it?
Yes, we can.
Yeah, so when I open it, I don't know if you can see the notepad file I've opened.
No.
No, it's not showing.
Okay, let me share. Yeah, so when you open that notepad file, this is what find, and this is all metadata file. So it will give you, this is what I was showing you, the date and the time. It shows you the sensor, and you know it is Landsat, the nomenclature Landsat, and this 08, then you know it is Landsat 8. It was Landsat 7, you'll find it as 7. It is Landsat 9, then you'll find it as 9. So this is the nomenclature of the file. You'll know it is Landsat 7, level 1 data. That means it is not processed surface reflectance. It is just raw data, Dixon number, values. And then this is the raw and path that you use in while downloading. And then this is the image, the file collection, the date at which the file was created, was the image acquisition date. And this is the date. What is this? 2017. This is when the date, the file was processed to that level 1. So this is just the nomenclature of the file. So the metadata is all there that you can see. It is very much, if you're interested in thermal remote sensing, then you will know you will only be looking at band 10 and band 11, that is for Landsat 8 and Landsat 9. And then one of the things that we'll use in converting those digital number values to temperatures are these thermal constants. You also find them in your metadata file, which is K1, K2 for each band, band 10 and band 11. I've not gone to the algorithms. That's why I want you to, if you're interested, to go and read further the algorithms of how you convert from digital number values to temperature values. So all the information that you need to understand about that data is within the metadata file. So that is how you get the metadata. When you download it, it comes with.
Thank you. Maybe another one on the when you've downloaded that zip file, could you give some interpretation of the context there? Last time we downloaded and we did
when
to
you
some
have
the downloaded zip file, the components, maybe just to give an insight into what is contained there and the meaning.
It is what I was showing you previously. When you download an image, yeah, it will come as this. It is this zipped folder. Of course, you will differentiate it from here. Landsat 8, level 1, raw and path, and the date. When you unzip, then you have all these small files coming in. And they are small files because remember, Landsat 8 has 13 bands. So it will create for you all the 13, but each band comes differently. So we said for Landsat 8 and 9, the thermal sensor takes up 2 bands, which is band 10 and band 11. So when you're doing an analysis on satellite, on Landsat 8 or Landsat 9, you will only be looking at band 10 and band 11 for your thermal remote sensing. So it's a zipped folder, but when you unzip it, then you have all these bands. It's up to you to know what kind of application I'm doing and what bands are going to be applicable in my application. That is it.
All right.
So, yeah.
Thank you very much, Christine, for this lecture. Very interesting lecture. And I hope the class have appreciated what thermal remote sensing is about. And remember, in remote sensing, especially for the mapping application, what we're interested in is being able to distinguish different features. And as Christine has said, different features will have different emissivities. And that's what we want to leverage to be able to distinguish one feature from the other. Application areas are numerous. In the context of Plan B, we don't have the time to explore all the options. Maybe next week, if there's time, I might invite somebody to give a talk about how they've leverage this work for their research, and we just open. We'll see how that goes. But as I mentioned at the start, our first lecture was really about, our first lectures have been about optical remote sensing. Today you've got a flavor of thermal remote sensing, and tomorrow we shall see radar remote sensing. And Dr. Makabai will be giving that lecture, and hopefully for Aisha, you'll be able to see how it can be applied also for your geological applications. But not only geological applications, but lots of other applications as well. As you probably saw from the lectures, all surfaces will behave differently in different portions of the spectrum. So we have seen how vegetation behaves in optical portion, the visible portion, how it behaves in the near infrared. Today you've seen how it behaves in thermal, and tomorrow we shall see how it behaves in the radar portion of the spectrum. So, and have a great evening.
Thank you, Doctor, and thank you, Christine, for the presentation.